Good. We're going to do one more survey calculation this hour, and it's going to be essentially a solid liquid equilibrium survey calculation. What we're going to do is we're going to take something very simple. It's going to be nickel, okay, nickel oxide, actually, nickel hydroxide. And we're going to study its solubility as a function of pH. And the reason we're going to do this is, again, just to give you a glimpse of how you can look at multiple systems simultaneously. But at the same time, we want to show you the properties of what we call transition metals. Again, remember, always in these training classes, we always want to show at least a little bit of the chemical properties of the periodic table, just so that you're not surprised, so just so you at least have a glimpse of it, especially if you don't get to use it regularly. And nickel is right smack dab in the middle of the periodic table, okay? And it's called a transition metal, and it has some interesting behaviors that is characteristic of that part of the periodic table. Okay, so what we're going to do, and I just want to show those to you. So let's go ahead and add a new stream. Okay, and we're going to call this thing nickel speciation. You're going to add NiOH2 to the inflow list. And again, we're just sticking with moles here. Moles is a great way of learning the software, because you don't have to think about milligrams per liter or constant or other types of units. You're just focusing on the mechanics. And we're showing examples that have stoichiometric relationships, like one mole of acid plus 1 mole of base equals 1 mole of salt, that kind of thing. But that's going to change in about 15 minutes when we start looking at water analyses. Okay. Then we do have to start thinking more realistically or more practically about units. Okay, so we have nickel hydroxide there. We're going to give it just a simple value, 0.02 moles. Okay, just a simple number, maybe a little bit arbitrary. And now you're going to add a calculation, and it's going to be a survey. Now, the survey you're going to do is going to be a pH survey. So you've seen pH surveys before. We've done it already. So survey by pH. Okay. We already know what happens in the grid. You get a set pH showing up as calculation type. It asks you, are you okay with these acids and bases? And the only thing left to do is to set the conditions of the survey. So you click on the specs button. We're going to start with HCl and with caustic, as we know already. And what we're going to do now is go to the survey range. We're going to set the start at, let's say, 2 pH. Okay, I don't think we have to go down to 0. We're going to end at 14, but we're going to go by essentially 0.2 increments. I'm sorry, let me do that again, 0.25 increments. We don't need that many points. So we'll go make 48 points, or 48 steps rather. Press OK. And now the software is ready to run. You can see the calculate button is green. We set the conditions of our survey. We set our initial composition. We're using the default conditions, temperature and pressure, right? Press calculate. Now, the calculation's happening. As we learned before, we know that the dependent variables in the plot are going to be the acid and base used. So we know that we're really not interested in that. We're going to change that out in just a second. Let me make sure everybody's with me. Did everybody get the calculation done? Or is everybody doing it right now?
Yeah, it's done.
Beautiful. Let's now go to the variables. First of all, let's just get rid of the caustic and the HCl. We don't need it. And let me again give you an explanation of what we want to do here. Okay, we've taken nickel hydroxide. put it in water. Odds are it precipitates out. You've got solid forming at the bottom, and you have a solution containing a little bit of nickel in there. Then I start adding acid to it. It causes essentially nickel to redissolve in the water. Right? Or I add base to it. It either can make it even less soluble, or it could actually make it redissolve. What I want to find out is, as I'm adding the acid or base and changing the pH, how does that change the behavior of nickel, that precipitate? Does it cause it to dissolve? And if it does dissolve, what does it look like in the water? What are the species that exist in the water phase? So we're going to do one thing first. And there are actually a couple of things that are important here that I can show you. First thing we're going to do is look at it from a solid standpoint. How much nickel remains as a solid? So I want you to expand the solid section, double click on where it says nickel hydroxide, and add that to the y-axis, and then press OK.
Sorry, Adrian, I didn't put any quantity of nickel.
Oh, no problem. Go back
Could
to
you tell me which quantity?
Yeah, go back.
0.02.
Yeah,
Perfect.
go back to just add 0.02 moles of nickel hydroxide.
Perfect, thank you.
Sure, and just recalculate. It's a pretty quick calculation.
Yeah.
So what we see here is that nickel hydroxide exists. There's two phases that are present. There's the water phase and the salt phase. But as I get to about pH of 6.5 or 7, that nickel hydroxide starts to dissolve. And by the time I get to about 6.75, there's no more nickel hydroxide left. It's all dissolved in water. That's one thing we're pulling from this study. I do want to just show you what happens if you click on View Data. Okay, if you click on View Data, rather than seeing the plot, you're seeing the XY data that creates the plot. Okay, so just keep that in mind, that you can look at the information two ways, either at the plot way or by actually looking at the XY data.
The view plot, AJ, is exportable to Excel. You can basically highlight that, copy and paste into Excel, some other package,
That's
statistical package or whatever.
Right. You can copy. Okay. Right. There's several ways of copying it. Right. So you can. Here's the copy. Or Control C. In the view data, you can also copy this and Control C, Control V.
Yep, and you can copy only one column at a time instead of two, and you have all these options, right?
Yeah. Mm-hmm.
Okay.
Copy one at a time. Yeah. Good. Okay. Next, I want to find out, well, why did nickel decide to dissolve, and what is happening chemically below pH of 7 that causes nickel to dissolve? And the only way to understand that is to look at what's going on in the water phase itself. So go back into the variables list, remove the variable from the Y1 axis, the nickel hydroxide. And then you're going to expand that liquid 1 section. And just like Dino was saying, if I had the ability to say groups, add all the nickel species to the y-axis, right? And this was where it would help again, Dino. Since we don't have that, you're going to double click on every nickel containing species in this.
AJ, can that not be done in MBG total liquid 1?
We're going to get to that later. Yeah, but I want to get to that later. That's different. MBG is the total concentration. But yes, you'll see that in just a second. So for now, let's just look. What we're going to do is look at the individual species that add up to that MBG. So that's what we see. Problem is, just like we saw before, that there's one variable that essentially dwarfs everything else. So it's a case where we have to turn this into a log plot to see everything. Okay, so right mouse click on the y-axis and select log scale. Now, the problem with this plot is you can't look at it and say, well, I can remove it. I've got 40 orders of magnitude here on the y-axis. How can I reduce this? And like I was saying before, you can right mouse click and remove. It's really not a good idea here because a lot of these things are important depending upon pH. So what you can do instead now is you can use the zoom feature in the software. These buttons up here, these 3 buttons are zooms. If I were to create a box, I'm clicking, left mouse clicking, and then just drawing a box around a certain fraction of the plot. And eventually I'm going to unclick it, depending upon where I think it's a good place to stop. Right there. I'm going to stop at 10 to the minus 13 and press OK. What that does is it zooms into that section. So it actually stopped at 10 to the minus 14 to 10 to the minus 2. And when I did that, you may or may not have seen this, but it activated these buttons up top here. This here is to reset the zoom. This here is to shrink it out further. And this is to shrink it out, to increase the zoom. Okay. But now what I can do is at least say, okay, I'm going to zoom into this area so I can understand more clearly what's happening.
Hey, AJ,
Mhm.
I don't know if this capability exists or not, but worthwhile to ask you. Have we considered doing, since we have a log scale here, which is really a semi-log here, have we considered doing a log and specifically a base stand because of the pH?
Yeah, you could.
So,
But instead of having, since the pH is just the activity of the proton,
right.
you could replace this. I'll just answer your question quickly here. You can
Yeah.
get the liquid 1 proton, put this on the x-axis, and then you'd have what you're looking for. It's not perfect because this is the concentration, not the activity.
Yep.
Nevertheless, at least it's close to what you're looking at.
Yeah. It give you a smoother plot, at the very least,
Sure. Okay. Okay, good. So what I just zoomed back out, but again, if I wanted to, I could zoom in. It's like that. Or I can always go to the right mouse click on the Y axis again and click on adjust scale. And in adjust scale, I can in fact set my minimum. 10 to the minus 14, press OK. And now that's my plot. I didn't zoom in or out. I just forced the scale, just like in Excel. You have your minimum and your maximum. Good. What is important for us to note, at least from a chemistry standpoint, is that, and I'm just going to go back to my original scale. You guys can play with it however you want. I'm going to do it this way for now. And then what I'm going to do is I'm just going to start removing stuff that I know I can get rid of that isn't going to help me with the explanation of what's happening. Just a couple of things I want to get rid of here. And you don't have to get rid of them yourself. It's just that I want to get rid of them. Okay, good. And then I'm actually going to zoom in between pH of 7 and pH of 14. Also, right here. All right. So what I want to get to is this. If you look at the stuff, just look at my screen right now, although you can look at it on yours as well. Look at what we have as, well, look what I used for variables. I've got nickel +2 in the triangles. That's essentially the nickel ion dissolved in water. That nickel ion is important at low pHs. Essentially, it's nickel by itself surrounded by a hydration sphere of waters. Okay. The next important one is this nickel hydroxide +1. Essentially, that's nickel that coordinates with a hydroxide ion to form this +1 charge ion pair. That's also surrounded by water. Okay. At higher pHs, even though it's not as important, you can see there's a nickel hydroxide too. Ni surrounded by, coordinating with 2 hydroxides, and then surrounded by 4 more waters. At higher pHs, you have NiOH3, means nickel coordinating, bonding to 3 hydroxides, and then surrounded by 3 more waters. And then lastly, at very high pHs, You have nickel that's coordinated with 4 hydroxides and then surrounded by 2 more waters. So as you increase the pH, as the hydroxide concentration in the water increases, nickel, being a transition metal, coordinates with that hydroxide to form these new ions. At low pHs, since there's no hydroxide present, it's just the free nickel. As I increase the pH, you can see that you've got nickel hydroxide 1, nickel hydroxide 2, nickel hydroxide 3, and nickel hydroxide 4. And those are characteristics of what they call, you may remember this term, a Lewis acid. Transition metals have acidic behavior, but they're not a protic acid. They don't have any hydrogen ions to give up. But what they do instead is they absorb hydroxide ions. And in that way, they act as an acid, not by adding hydrogen ions to the water, but by removing hydroxides from the water. That gives it the acid characteristic. So the reason I wanted to show this example was, again, to show you how to manipulate the plot, get what you want, but also to show you that when you're dealing with transition metals plus aluminum, you'll see these hydroxide species. And these hydroxide species are characteristic of what they call Lewis acids that are part of that transition metal, and transition metals behave this way. Now, because
So, AJ, I'm sorry, quickly. So, Lewis acid or Lewis type behavior, is that the affinity of the transition metal to OH minus
that's
radical? Right. Is that okay?
It's not a radical per se. It's just the anion.
Yes.
It's just the anion. Yeah.
Yes. Sorry. The
it's
ionic
coordination. And it's a lot of fun if you're a chemist by nature or geochemist. You have a lot of fun learning about it. If you're not, forget it. Just say thanks, AJ. It's fun talking about it, but let's get to the next story. But what's cool about Lewis acids, transition metals, is it gives us the behavior we need. If it weren't for this type of behavior, for example, then and it just dissolved in water, right? Then we wouldn't have the ability to have like aluminum swings. This characteristic of forming like aluminum trihydroxide at moderate pH and therefore precipitating out to form a solid phase is why you form these films at atmospheric conditions, and aluminum doesn't corrode.
Yes, AJ, this is of specific interest, at least to me, in understanding scale stability. Not only with nickel-based alloys or nickel-based system, but iron-based system versus an iron oxide, an iron chloride, a sulfur oxide. Trying to understand that scale. It is a flaky nature or a stable nature, and what's the threshold for the scale to stabilize under certain conditions. That's of a specific interest and extremely helpful. And this goes to what you're talking about, the Lewis acid and their affinity to dissolve or not to dissolve. And so I may call you some other time to discuss this in further detail, if I may.
Sure. Absolutely, yeah. There's another piece to this discussion in the full 2-day class. What we would do is we would take this example, and then we would add either ammonia or cyanide to it. And what you would see would be that the whole solubility of nickel or some other transition metal would be completely disrupted because ammonia and cyanide create new dissolved complexes with the nickel, and it increases the solubility significantly. We won't do it here, but that's part of the larger discussion about the behavior of these transition metals in water with certain cations and anions, or certain anions. Okay, I do want to get to the point. I can't remember who was asking me about this. Faisal, may have been you, or maybe it was you, Brett, to look at the material codes. So now let's click on variables again. And now I want you to go to a section of the plot variables called MBG. MBG stands for Material Balance Group. It's essentially the element balance, the total element balance in a given phase. So for example, if I click on MBG totals here, liquid 1, and if I choose nickel +2 liquid 1, it'll tell me what the total amount of nickel is in the water phase. So let's go ahead and do that. expand the MBG totals, liquid 1, find nickel, double click on it so that it shows up in the Y1 axis, and then press OK. And what you should notice is that this nice, pretty curve shows up at the top of the plot, right? And essentially, this curve here represents the sum of everything else underneath it, right? So this concentration here is the sum of this ion plus this ion plus this molecule plus this ion plus this ion. So essentially, it summed up all the different species to come up with the total concentration of nickel in solution. And this is called like the solubility well of nickel hydroxide of nickel. And if it weren't for the solubility well, you wouldn't have a nice nickel patina or a passive film forming on your corrosion resistant alloys. Problem is, you get low enough pHs, nickel is no longer passivating, so you need to have chrome in there to form a chrome passive film. And that gets into the more of the material science part. I'm not an expert in that, but that kind of gets into, you know, what passive films are important under what conditions. Any questions about that? Okay, I do want to address the fact, you know, these are elements, right? Why isn't this called an element balance? Why do we call it MBG? The reason we call this MBG and not element, total element balance, is because we have to distinguish, elements can have multiple oxidation states. So we can't call them elements because I may have 5 different, you know, 8 different sulfur elements. So instead of calling them, and there's more to it than that, but instead of calling them elements, we call them material balance groups. But they're essentially the same thing. They're the element at that given oxidation state. Or they could be an organic base molecule, okay, like a methanol, like a CH3O base molecule that makes up methanol. But nevertheless, they still do the same thing. You select them, and it gives you the total amount of that particular element or material in that phase. And to make sure it's clear, you can see there are 5 phases present. The water phase, or the liquid 1 phase, the vapor, the oil phase, or the non-aqueous phase, the solid phase, and lastly, what we call the surface phase. Okay. Any questions about that? Okay, good. All right, now we're going to stop doing surveys. Let's go ahead and save the file. And we're going to jump into water analyses.